Welcome, everyone. I'm super excited to have you all here. I'm super excited to see familiar faces. It means that people are coming back, so they like what they see here. But also excited to see new faces. And excited to have people also watching us on Twitter. Welcome. The GitHub Security Lab, a few words about it, just one word about it. Get involved, right? You go on this page that is displayed on the screens and get involved. There are plenty of ways of getting involved in securing open source. We have bounty programs. You can contribute to sharing security knowledge, and you can come to this meetup and share with the community. To start, we will welcome Sam Lanning from the Security Lab with No More Walkable. Thank you.
Thanks. All right, so I'm going to be trying something a bit different and taking a normal 45-minute talk and squashing it down in 15 minutes. So I might be talking fast, so if I'm going too fast, sorry, but I'm not going to be slowing down. So my name's Sam. That's not working. There we go. My name's Sam. I am part of the Security Lab. I am a developer advocate of the Security Lab, so I do a lot of all the non-research tasks. Are often myself, Xavier, and Howard, who's a new person that's joined our team. Before working at GitHub, I was at SEML. I've been at SEML for 5 years, so security research and code queries is something I basically spent a lot of time doing. And I used to be a developer for LGTM, but that doesn't matter anymore. And here's stuff I like. Anyway, to start off with, I want to talk about a story of many bugs. This one starts off on the 7th of September 2017, where one of our coworkers, one of the members of our team, discovered a CVE or discovered a vulnerability in the Spring framework. Now, the way that this vulnerability worked is it interpreted user data as what's called a spell expression. And Spring had this expression language called Spring Expression Language, which allowed you to effectively evaluate arbitrary strings as code that you could use to evaluate or to access various Java objects. So if you could get control of one of these strings, you could effectively have a remote code execution. So that was very bad. So Mo discovered it and disclosed it to Pivotal. Pretty quickly afterwards, on the 21st of September, Pivotal published a patch that fixed the vulnerability, and they made an announcement that said everyone must update right away. The day after that, Mo had a look at the patch, saw it didn't fix the vulnerability because there was another path through it, sent Pivotal another exploit that caused an RCE. Day after that, or a few days after that, Pivotal, instead of going straight away and making an announcement, sent Mo a private message with, here's how we intend to fix it. Is it correct? Mo checked it. It wasn't correct. There was another path, so the library was still vulnerable. And then finally, after this, they decided that their approach wasn't really working, and they decided to refactor the entire part of the code base that was affected before pushing out a new patch and really fixing it this time. Let's talk about another story. This is also a story of many bugs. On the 27th of April, 2016, an RCE was discovered in Apache Struts where user data was evaluated as what's called an OGNL expression, which is similar to Spring's spell, where you can access arbitrary Java objects. So you don't, and it's, again, like spell, it's something that's designed to be used internally within the framework and not really supposed to be exposed. So this was pretty bad. You could get a remote code execution just by sending random HTTP data to Apache Strut servers. 12th of May 2016, Alvaro, over here, discovered another RCE that interpreted user data as a OGNL string. On the 20th of 16, another CVE, which interpreted user data as an OGNL string, allowing for remote code execution. 19th of March, another RCE allowing remote code execution by interpreting user data as OGNL. And again, on the 22nd of September. And again, on the 24th of September 2018. So you can see there's kind of a pattern here. And there's only so much space you can have on a slide, so I didn't include every single instance of remote code execution by interpreting user data as OGNL. Here are all the other CVEs. So we're having a bit of a problem in the software space at the moment where particular types of mistakes are being made over and over and over again. It might seem like I'm just making fun of open source projects here, but I'm really not. These are problems that are endemic across the entire industry. For example, Apple publishes part of the source code for Mac OS and OS X called the XNU kernel. And one of our other coworkers on the security lab team found a remote code execution in a component called the packet mangler. So he reported the vulnerability to Apple with a POC. They fixed the vulnerability. They pushed out an update. And then when they later published the source code for the latest version, because they didn't actually do all development out in the open, they have snapshots of their source code, Kevin discovered that there was still a bug in the same block of code. So he sent them a new exploit that triggered the vulnerability, and then Apple then had to fix that in a later release. So let's see, how do we solve this problem? What if we use information of when we get a new vulnerability to see it as an opportunity? If we have, once we have found a specific type of mistake, is it an indicator that there are potentially similar mistakes made elsewhere throughout the code base? For example, your use of C may increase your chances of having certain types of memory corruption issues, or using something like Apache OGNL or Spring Expression language might make your code base more vulnerable to certain types of remote code execution. So you should try and find similar mistakes and not just fix that one instance that you have been made aware of. And companies such as Google and Microsoft have actually been doing this for quite a while now, and they call this process variant analysis. So variant analysis, and in a blog post that Stephen Hunter talks about this process, he says, after doing root cause analysis, our next step is variant analysis, which is finding and investigating any variants of the vulnerability. It's important that we find all such variants and patch them all simultaneously, otherwise we bear the risk of being exploited in the wild. So for large companies like Google and Microsoft, not looking for other variants, not looking for similar mistakes is simply not an option, because if they don't do that, when they release a patch, other people will take it upon themselves to try and find similar vulnerabilities in the code, and if possible, exploit them. Sometimes having to reverse engineer a patch, or just looking at source code if there are source code releases. So how do you do variant analysis? How do you find similar mistakes? Well, to be honest, until recently, most of the big players have been predominantly relying on a lot of manual work by their security response teams. Hands up anyone who's on a security response team. One or two, okay. So you might have certain techniques like looking at particularly sensitive areas of the code base that are more likely to have vulnerabilities, or manually checking how data flows through an application using techniques like control flow or data flow, checking the range of values that certain variables can take, ensuring that their bounds are being checked correctly. You quite often make use of text search tools like grep or AWK. You can also make your life a little bit easier if you use an IDE or something else that's language aware like SourceGraph, where you can use jump to definition, find references quickly to certain functions, and jump through the call graph really quickly. But as you can imagine, doing this sort of manual analysis, especially on a regular basis, can be quite difficult. It's repetitive and time-consuming. It requires lots of iterative exploration. Manually checking a code base is very prone to human error, so the more complex the mistake that you're looking for, or the larger the code base, or the closer the deadline, the more likely it is that something will be missed, which is not very good when it comes to security. And it's also just not scalable. As the size of a code base increases, manually checking for a specific class of vulnerability every time a new one is discovered becomes infeasible. And as your list of types of mistakes that you need to check continues to grow, then the things you need to check at code review time also increases, which either makes code review process much slower or inaccurate and insufficient. On top of that, even in the most high-tech companies, the number of full-time developers far outweighs the number of people working on security full-time. So we just can't expect these security teams to keep up with all of the code being written. So what can you do? If variant analysis is critical to ensure that your applications are secure, yet doing so isn't feasible. What if there was a way of automating it? What if there was a way that we could describe a particular mistake that lets us automatically automatically find it by scanning a code base, using not only syntactic information, but also semantic information like call graphs, data flow, control flow, that sort of thing. We could then run them across the entire code base, run them across multiple code bases, and also run them into the future to prevent reoccurrences of the same mistake happening again. So it turns out there are actually a few tools out there that allow you to do exactly that. Clang Tidy, for example, that's part of the Clang compiler, can be extended to write rules for C++ that can take into account both syntactic and semantic information. And Mozilla have actually got a custom set of rules that they run against every patch that's submitted to Firefox to catch any new mistakes. And linters as well are starting to include more and more semantic information for their rules to use, particularly those that work with statically typed languages. There's also projects like Continental, and there are a number of technologies emerging that allow you to interactively write queries over source code that include some semantic information, including a solution by GitHub, CodeQL. So I'm going to quickly go over an example that uses CodeQL from the same Microsoft blog post earlier. So, how many people in the room are familiar with C? Great, cool. I won't dive too deeply into this, but I'll give a quick, brief overview of this. How many people are familiar with C and JavaScript? Cool. So this is a illustrative snippet of code from the Chakra code base, which is Edge's and Microsoft Windows JavaScript interpreter, which is going to start being used a little less now that they're switching over to the same engine as Chromium. But still, at one point, this is a very important piece of software they need to secure. So this particular bit of code has a vulnerability in it. And it's called when it's a certain primitive method built into JavaScript that you execute, and it deals with array buffers. So what's going on here is you are allocating, or you're getting the address and size of a particular block of memory that represents an array buffer in JavaScript. You are then calling a method that can potentially run JavaScript code. So this particular method is used to try and get the value of method of the particular thing that was passed to it. And with this, you can actually overwrite the value of method in JavaScript to run arbitrary JavaScript here and potentially change the value of the array buffer or change the contents of the array buffer, at which point buffer size and pbuffer now reference memory that's invalid. Pbuffer is now a dangling pointer. And buffer size refers to the size of the array buffer used to be, but it doesn't really mean anything anymore. So when you actually try and do something with this buffer and size value, you have a memory corruption vulnerability. So Microsoft, before I go on to that, this is what the JavaScript exploit kind of looked like. You just overwrite value of and say, hey, do this thing instead. So Microsoft assessed this vulnerability as critical, and they wanted to know if they had any similar mistakes anywhere else in the Chakra code. So they wrote a query using CodeQL that basically describes the pattern of assigning a pointer to an array buffer, the pointer of an array buffer to a value, calling back into JavaScript, and then using that value. This is what the query looked like. I won't go over it now, but you can come find me and I can describe how it works later. But when they ran this query, in addition to the original vulnerability, they found 4 variants that they also assessed as having critical severity. So that example was pretty specific to Chakra code, but there are also much more general cases which you might want to write queries for. One example is zip-slip. Who here is familiar with zip-slip? A couple of people. I'm always surprised with how few people know about zip-slip. Okay, so zip-slip, I'm just going to skip through here. Zip-slip, like all core vulnerabilities, had a logo. The way this worked is, so zip files are structured a little bit like this. Even though they contain a directory structure of files, they don't actually have a tree format. They're just a list of entries where each entry has a name or a path, which is just a string. So there's a lot of code that implements extracting zip files, which just concatenates the path to a destination directory, which might be problematic if there are paths like this in the zip file. Who here knows what would happen if you try to unzip something like this with concatenating the string? Yeah? Just nod if you think you know what's going to happen. Cool, I've got a few nods. Yeah, it's bad. You will end up unzipping stuff outside of your target directory, which could potentially have security implications. So, for example, if you're running a unzipping application as root and you unzipped to that bottom one there, you could potentially add an entry to the cron tab, which would then allow you to run any arbitrary code on the server as root. So Microsoft wrote a query for it, and they found a bunch of vulnerabilities. This is what a vulnerable code looks like, and this is what fixed code looks like. It's like a one-liner to check and prevent any vulnerabilities using this type. But there's a lot of code out there that we've been able to find that has zip-slip vulnerabilities, which is pretty much every programming language has code that does unzipping. Anyway, that's more or less all I have time for. There was more, but I was too slow. Thanks. Oh, yes, and you're up next. Cool.
Welcome, Michael Scovetta now from Microsoft.
There you go.
Testing, cool. All right, open source is awesome. Everything that you use, everything you have in your pocket, everything you use every day has open source. Open source is great. It has changed the world. Most open source projects, though, assume trust. They assume that people are generally lawful good, that they want to cooperate, that they want to do the right thing. This is good for the community. It's great for innovation. We want this. But attackers know this, and attackers take advantage of this. So attackers are willing to exploit the trust that you assume that you have in the open source projects, and it exploits the trust that open source projects have amongst themselves. When you depend on something else, you're not expecting that dependency to be malicious. My name is Mike Scovetta. I run an open source security team at Microsoft. My job, my team's job, is to make sure that our engineers can use open source everywhere, that they can take the maximum advantage that they can from this, that they can develop products and services of amazing quality, delight our customers, and all of that, and avoiding the security risks that inevitably come with using open source. I love open source. This is not a boo open source presentation, but I want to talk to you about backdoors today. So what is a backdoor? We could argue for probably hours on a precise definition. For the purpose of this, a backdoor happens when an attacker tries to hide a malicious or sort of malicious component in something, and somebody uses it. So it's hiding something. The victim here is usually a software engineer. Sometimes it's an end user. Sometimes it's a build system. But it's a little bit different than traditional malware, antivirus kind of stuff. So the beginning of time for backdoors, at least in my opinion, was July 2018. This was ESLint Scope. Who remembers ESLint Scope? Okay, so ESLint Scope happened, an attacker compromised a developer's credentials, published a new version of the ESLint Scope module on NPM. The purpose of this module, the only thing that it did, well, the only additional thing that it did was slurp the developer's credentials from their NPM RC file and send them off to a stat counter website. So it was caught, thankfully. But when we looked at this, we started asking ourselves, the NPM ecosystem at the time was 600,000 or 700,000 projects. Were there any more out there? If I were an attacker, would I just compromise one, or would I compromise like 50? So we were really trying to answer how many more were there out there, and could we find them all? So we had a hypothesis that we could do this stuff efficiently using code QL, literally. So we wrote a query using SEML at the time, but code QL, and it looked for one pattern that was apparent from the ESLint scope malware. And that was untrusted data coming in from the web and getting executed. So specifically, we were looking for, within a JavaScript program, data coming in from HTTP GET or POST, flowing through the application, and then landing in child process.exec. So we ran this over 50,000 random NPM projects. We found 14 that matched the pattern. Usually, for anybody that's used static analysis, you'd expect out of 14, 0 would be real. I mean, there's usually a very high false positive rate for most static analysis tools. They were all accurate. They were all true. We reported these all to NPM. They've all been fixed. But here's the takeaway here. None of these were malicious. These were just ordinary, run-of-the-mill, concatenate a string together and pipe it and send it to exec. The developer made a mistake. It wasn't malware. It was just a vulnerability. But then April 2019 happened, and this was Bootstrap SaaS. Bootstrap SaaS, basically the same kind of thing, but this was a backdoor that was inserted. This was very intentional. The way the backdoor works is the attacker, once the attacker knew that a vulnerable version of Bootstrap SaaS was running, they would pass a regular web request with a special cookie. The cookie would have a base64 encoded command, and the library would see that and just run it. So that was downloaded 1,400 times before it was found, and everybody said, yay, well, at least we caught it. Did we catch it? Did we catch them all? So we downloaded every RubyGems package, and we had to write our own analyzer for this because CodeQL doesn't scan Ruby at this point. Looking for basically this. A cookie gets decoded and then evaled. So we ran this on a very, very high-end Azure VM. We found 2 additional backdoors. So the top one on the right is the Bootstrap SaaS. And you'll see there the CFD UID is the name of the cookie. That gets base64 decoded and then evaled on the next line. The one on the bottom is from a project called RubyTree. Same thing. And then again on Simple CAPTCHA 2. This was slightly different, but it did the exact same thing. So we looked at the projects themselves. And the thing you'll notice here is the RubyGems project, the versions match the releases on GitHub up until March 2019. That's when a new version was published on RubyGems, but not on GitHub. So we saw this, we said, okay, his RubyGem, or his or her, RubyGems developer, RubyGems account credentials were popped, and the attacker came in and published a new version. We reported this to the RubyGems security team. They took it down in 14 minutes. That is amazing response. Huge kudos to them for that kind of speed. And that was it. Well, it wasn't quite it. We saw this pattern. So the Bootstrap SaaS backdoor was found at the end of March. Notice the date here is March 16th. So the 2 that we found were actually predated the one that went public by about 2 weeks. So we thought, well, maybe we're not looking back far enough. Maybe there were more out there. And we saw this pattern of a newer version in RubyGems than on GitHub. So we looked at all of the projects, all RubyGems projects that had a GitHub account where the tags, there was a newer version than there was a release on GitHub. And there were about 300 or 400 published over that month. And we looked at every single one, and we just found the 3 that we knew about: Bootstrap, Simple Captcha 2 and Ruby Tree. So we felt good. We felt like we nailed that. But we have a problem. We've spent weeks doing this work, and we can't play whack-a-mole. So we need to do the stuff at scale. We want to continuously scan packages as they get published for certain things. What we're not trying to do specifically is run every static analysis rule for every vulnerability on every package all the time. That's important. We need to do it. That's not the purpose of this experiment. This was, can we catch the really egregious stuff, the stuff that I want to be woken up if it happens? So libraries.io has a really useful API. It lets you just query for packages ordered by publish date. So if you do this and look for publish date, if you, let's say, query it every, let's say, 30 seconds, and you sort it by most recent, you can get effectively a stream of newly published packages. So this is what we do. So I have this thing running. This thing had been running continuously for about 6 months, and we found about a dozen backdoors. So here is, as I was preparing this presentation, I realized that I actually turned it off for a few weeks because I was getting really high. I was getting like 1,000 messages a day. So I turned it off, and then I remembered I turned it off, so I turned it back on, and literally 2 hours after I turned it on, I got this email. And what you probably can't read on the screen up there, this is, the way that this analysis works is just grep. So it looks for curl in npm packages.json install scripts. The idea being, as soon as you install it, you get owned. And in fact, you do here. So the third, fourth, and fifth lines there, what this is doing is it's curl, and then takes your environment variables, and then what you can't see at the very end because it's cut off, is it sends it to npm.1337qq.com, which is totally authentic and inspires trust, right? So we got this report. I think the package was published about 1 a.m. I got the report at 2 a.m. I woke up at 7 or 8, reported to NPM. They removed it by 10. So again, awesome response from Andre at NPM Security. And strangely, like this was the one that like ZDNet started writing about. So this one has gotten some attention. I feel good about this because it's a problem, and we over the past 2 years we've probably found 100 of these, and this was the first one that really got picked up. So I feel like the attention is on backdoors, and we're going to improve the world, I guess. So that's backdoors. But there's a similar thing about typo squatting. So everybody knows what typo squatting is for domains, where you want to go to PayPal, but you go to like P and the A is a 4, or it looks like it's a 1 instead of an L. Same thing happens for packages. So this started off really slow, and then I'd say about a year ago it started to pick up. So just last month there were a few found on PyPy. This was Python 3-dateutil, which happens to be the module name in Ubuntu, or apt, but not the real one, which is supposed to be dateutil. And the other one is jellyfish, but the L is like a Cyrillic L, so it looks the same, but it's not. So about a year ago, we started doing more serious research on this. And we built an algorithm and a service and have all the data that compares projects by name first. So we look at Levenstein distance. We look at keyboard distance because it's more likely that you'd fat finger a E when you mean a D than you would an O. Prefixes and suffixes, things like that. So I'm a big fan of Django, so the first one I did literally for this presentation was Django. And those were the 5 that came up. So the first one is Jamgo, then there's Django X, Django, Demango, and XDjango. 4 of those are totally legit. Like, they happen to have a name that's really close to Django, and some of them, they're related to Django. But that first one, Jamgo, what does that look like? Well, it's a cool framework for install a typo-squatted package busted mister. It doesn't actually do anything, so it wasn't malicious, but it's not what we want. So we emailed the Python security folks, and they took it down, and now it's gone. So, but these, we tend to get these in clumps. So these are three stories about three different types of typo squatting. The first one, this was the first group that we found, was an author on NPM that took all of the top 10 most downloaded NPM modules, and they created like 100 variants of each, or not 100, I guess it would have been like 9 variants of each one. So chalk would be like cholk, and Lodash would be like La-dash, and things like that. And each of them, what the typo squatted module did was just import and then re-export the authentic module. So it sat in the middle as a shim. But was it doing anything bad? Well, no, but the author could just rev the version at some future point and do something different. So we think this was an early stage attack. They were setting the groundwork for something. So we got those removed. The second group was a group of 72 typo squatted modules. These did this, they actually copied the code from the original module and then just added one line of obfuscated JavaScript that just tried to transfer your Ethereum to their wallet. So we got a bunch of advisories out of that. And the third one is in the PyPy ecosystem, there's a security researcher that proactively is typo squatting about 1,100 packages. Each of these packages, they don't do anything. All they do is print, this is not the right module, go here instead. So is this typo squatting? Well, yes. Is it malicious? No. Should we do anything about it? There is a gray area here. So we talked about vulnerabilities, we talked about backdoors, we talked about typo squatting. I've got a couple takeaways. It's really just one takeaway for if you're an author. Use two-factor. All of the backdoors, all of the backdoors were the result of compromised credentials. Using two-factor pretty much solves that problem. Yes, SMS isn't perfect. It's certainly better than just having a password that you reuse everywhere. Tokens are fine if you're protecting them. Don't check your tokens into source code and all that. And make sure you use it for both your source code repository, GitHub, and wherever you publish to. If you're a user or a consumer of packages, it's much harder. Just being aware that there is this threat out there, I think, can be some help. Watch your spelling when you're typing a module. The number of downloads is a pretty good indicator. If you're using a module that has 4 downloads, be really, really careful. Like double check. Things like NPM audit is also great. Whatever you can automate, get these alerts. So in the future, someone finds out that something was typo squatting or malicious or whatever, it gets taken down. You use NPM audit or the other equivalents, and you get notified. So that's all I have. And I'm sure I'm out of time. So I'll take questions after. Thank you.
Thank you, Michael. And next is James Forshaw.
Fantastic. Everyone can see all right? Okay. I'm James. I work at Google in the Project Zero team. So I look for security vulnerabilities primarily in Windows. Microsoft products are my specialty. And I mainly look for privilege escalations. So what I'm here to talk about today is some of my tooling for finding vulnerabilities, local privilege escalation vulnerabilities in the RPC attack surface of Windows. So there's no slides for good or for bad, but I'm just going to demo the tools in the next 10 to 15 minutes. So when I find my vulnerabilities, I have to write some sort of proof of concept. And I really like writing my proof of concepts in .NET mainly because I'm lazy. I really want to have the least amount of effort possible to write that proof of concept. And C#, .NET generally gives me that flexibility rather than having to write everything in C++ or some other equivalent language. Now, when it comes to RPC attack surface, there was a problem. The tooling which really is available is primarily focused on native code. All the libraries Microsoft supply on Windows are designed to be interacted with from native code. And that, of course, is a problem. I can do pinvoke in .NET. That's something I can easily do. However, even then, it becomes a very difficult challenge to implement RPC efficiently in .NET, pinvoking into native code. So this is what you would normally see if you're writing your C++ application or your C application. You have some sort of server IDL file, your interface definition language file, and you push that through the Microsoft compiler, and what comes out of it at the other end is all this stuff. And technically, you could probably parse this and convert it into your own format, but it's just going to be a pain. So I have a pre-existing module. Of course, we're here for the GitHub Security Lab meeting. And, of course, all my tooling is open source, and it is available on GitHub. So this is my sandbox attack surface analysis tooling. And it's designed to do various different things. It was originally designed to search for accessible resources, so files, processes, things like that, from sandboxed processes, so from Chrome, from Edge, from Firefox, those sort of things. But you can use it for more general use. So it allows you to do attack surface analysis from a normal user account, so not just a sandbox account, to, say, system, which gives you your privilege escalation. And if you look through this, of course, it's all written in .NET. And I also have a PowerShell module, which is the thing I'm going to be demoing here. So the main thing, of course, is we can import our PowerShell module. And there's loads and loads of commands in here. Exported commands. Oops. Or to do loads and loads of different things. But, of course, I'm just going to focus on the RPC stuff. So the first problem with RPC research is, of course, I showed you that IDL file, but that IDL file is only available to the original developer. Obviously, I work for Google. I don't work for Microsoft. I don't have Windows source code. Therefore, how on earth am I going to get that RPC information to even do an analysis of it? So the first thing I had to write was a way of parsing an existing DLL or an existing executable, extracting its RPC server information, and then sort of constructing a object-oriented, sort of an object model around that, so that you can query it and you can do information on it. So I'll just one of the sort of classic examples of an RPC service is UAC. So when you do UAC elevation prompts, that's all going via RPC under the hood. So I can just call my get RPC server command, pass it the name of, say, the appinfo service, which is actually in appinfo.dll. And then I can pass it, it will also take symbols to resolve public symbol information. So it will actually try and resolve the names of every function, which of course is kind of useful if you're trying to analyze these things. So I run that, and I find I've got 5 RPC services. This information here is just giving us a basic idea of, you've got the unique identifier, which is how you connect to the RPC service, the version information, which is also part of that, the number of procedures, whether it can see any endpoints, and whether it's actually seemingly running. So the app info service is almost certainly running. So from a basic analysis perspective, I could, for example, use filter that out. So filter RPC server. And I just want to look for any RPC server which may happen to have the string process in one of its function names. And of course, doing that, we reduce our list down to 2 instead. So once we've got that, we obviously want to see what these RPC services are doing. And it turns out that because I'm parsing this RPC server information, it contains order marshalling code, which is responsible for sort of taking a C function call, marshalling it up into this NDR protocol, this network description representation protocol, and then pushing it over in the local case ALPC, which is a local RPC channel in Windows. This could be like named pipes or it could be TCP, but in this particular case it's ALPC. And then, of course, the server has to then unmarshal it again and then actually execute the program. And the advantage of this is because it's actually using like a bytecode representation for the most part, you can actually reverse engineer this bytecode representation and reconstruct the interface that you expected originally. So I can just, if I just capture that again, so I've only got my 2, just to make it slightly less horrible. I can do format RPC, not that one, format RPC server, and we actually now get a sort of pseudo C#, pseudo C versions of our interfaces. So it includes things like structure definitions. Now, of course, notice that these structures have no name, and that's because the bytecode doesn't store the names for these. The function names are only there because I know where the function is implemented in the server, and I can actually use public symbol information to extract that out. But of course, we've got, for example, launch admin process, and launch admin process is the like core function in UAC which does the elevation prompt. And that's great. Okay, I could potentially take this code, try and compile it. This in and of itself won't compile because this is sort of more for informational purposes than anything else. So, of course, I needed some way around that. So if I do this, I can call getRPC client, pass it number 1, which is the standard RPC interface. Run that. Nothing seems to be particularly interesting. But now what we've got is a .NET class which implements all those functions. So we can pass it to getMember. And so now we can see, for example, RAI launch admin process, which is there. And, of course, it has, obviously, all the parameters constructed, all the structures are in there, and you can actually start calling this function. So finally, we can do connect RPC client, pass it the client we want to connect, and now we've actually bound to the RPC service itself on Windows. So in this case, this is using this particular endpoint, which is this ALPC endpoint. You've now connected to it, and you can actually now invoke methods on it. So I could do RAI disable elevation service, and this will probably tell me, oh, you've got some sort of error result from that back. So NT status 1314. A required privilege is not held to run this. So, of course, I'm not allowed to call that function. But what you've got now is you've got .NET representation of RPC. You can do reflection to analyze this and generate fuzz cases for your RPC services. The beauty of this is it's all implemented. There's no native code, pretty much, between... I need some native code to do ALPC, but there's no native code responsible for the RPC marshalling. So if you pass the wrong value to the RPC function due to your fuzzing, or the worst that will happen is you'll get a managed exception from .NET, and you can catch it and carry on. And you won't get like a hard crash, which is a reasonable expectation if you're trying to write this using the native libraries. See if I do have a more thorough example. So I should actually be able to run a UAC prompt. So this now parses the RPC server, actually fills out some of the names. You can actually rename the structures so that it sort of gives you a better idea of what you're trying to call. And then I've defined a start UAC function, which hopefully should start a UAC prompt. Let's see if it actually works. Start UAC. Oops. And then I want to say, I don't know, we'll try and run Notepad elevated, and give it a command and start flags, and then run as admin. Okay, just in the down, and now we've now invoked over RPC. It's all done at runtime. There's no there is technically an assembly on disk, but it's all done at runtime. And you can just actually extract that information if you want to. If you want the C#, you can just do format RPC client. Oops. I killed that format RPC client. And this is actually now the C#, and you can actually then compile it into your own application. And I have actually, this is also on GitHub, wherever it is, Windows RPC clients. So this is also on GitHub, and this contains every client I could find on Windows 7 through Windows 10, 1909, all pre-compiled into C#. For your use, you can just pull it in as a library and just try and play with RPC on Windows. So that is the end of my time. I will be around for a little bit afterwards, but of course, thank you very much for listening, and hope you find it useful.
Thank you, James. And now, next is Alvaro Muñoz.
Okay, so time for breaking some SAML. My name is Alvaro Muñoz. I recently joined the GitHub Security Lab. By recently, I mean yesterday. And I did this research with Alexander, which cannot be here today, right? So breaking SAML is nothing really new. It was broke in the past. Probably the two more important attacks on SAML were the XML signature wrapping attacks and the attacks with XML comments discovered in 2018. Both of them were not successful against the SAML implementation in .NET, and also they required to be able to intercept a valid token and then modify that token by changing some specific fields without invalidating the signature. So this attack is capable of intercepting or crafting tokens from scratch, and you can actually generate any content for this token and then resign the token with your own public key and somehow fool the service provider into thinking that this key is valid and take it as a valid key. So a very brief introduction into SAML. Well, this was a 45-minute talk at DEF CON last year, and now I have to do like a very short version in 15 minutes, so just bear with me, please. Well, in SAML, you have a user that is trying to access a protected resource. And then this service provider is not handling authentication itself, so it's going to delegate the authentication into the identity provider. So it's going to redirect the user into the identity provider. The user is going to present the credentials, and upon verification of these credentials, is going to get an authentication token. So this authentication token, in this case, in SAML format, can contain multiple attributes, right? Probably the most important ones are the attributes that are also known as claims. And that contains all the information that the identity provider knows about the user that logged in, and that will be used by the service provider to make authentication and authorization decisions. And then we have the signature, right? If you don't sign the token, anyone, starting by the user, can change the token, change who they are and then pretend to be anyone for the service provider and then impersonate any user. So SAML is based on XML, and because it's based on XML, they didn't reinvent the XML signature standard. They reused that, and this is a simplified version of a SAML token. Basically, you have the assertion, that is the token itself. You have the subject and all the attribute statements that contains, as I said, all the information about who the user is, what's maybe the ID, the roles, email address, things like that. And then we have the signature block that contains the signed info, which basically contains all the information that is used to generate the signature. So things like the algorithm and things like that. Then you have the signature value, that is the signature itself. And what is most important for this research is the key info section, right? This key info tag. So if you go to the RFC, which is very convenient for this kind of research, you will see that, first of all, the key info is optional. Right, this is the RFC for the XML digital signature. It happens that the SAML format uses this standard, right? But in SAML, it's very common that the key info contains the public key of the identity provider. So that's probably 99% of the cases. Also, the XML digital signature doesn't handle the verification of the trust in the identity provider keys, right? So they only care about verifying that these documents, these XML documents, were signed with a given key. They don't care about if you trust that key or not. That's out of the scope of this standard, and it's something that has to be implemented by the library, in this case, that implementation of the SAML library. But what is more interesting from a security point of view is that if you have multiple declarations of keys within the key info section, they all should refer to the same key, right? So if you're a security researcher, that should be interesting to you, because what if I don't send the same key? What if I submit several keys and not all of them refer to the same key? So that's something that you want to try. So verifying the token, the SAML token integrity in .NET, it's basically two-step. First of all, we will extract the key from this key info section, and then we will use that key to verify the signature. But as I said previously, nothing stops an attacker from intercepting a token, changing it, resign it with their own key, and then there's this second step that we need to verify who is the signer of this token, right? Because otherwise anyone can resign the token and then just put their malicious content in it. So the second step is take the key info section again, extract or resolve a security token that is basically a representation of the signing party, and then verify that you trust that signing party. Right, so the strange thing in the implementation in .NET is that they are processing the key info section twice from scratch. So instead of reusing the key that was used to verify the signature and then verify that you trust the signing party for that key, they are taking the key info section again, processing it again from scratch, identifying the signing party, and then verifying the trust on that signing party. So we will try to abuse that fact by trying to get these two processes to return different elements from the key info section. Right, so what we need to do is to craft the key info element in the SAML token in such a way that it will contain two elements. Remember that the standard says that they should be referring to the same element, but nothing stops us from referring to two different keys. What we are going to do is trying to get the resolve security key, the method that actually returns the key that is going to be used to verify the signature, to return a key that is different from the one that is going to be used for authentication of the signing party. And if we are able to do that, then we will be able to bypass the verification of the integrity of these tokens. So we analyzed different frameworks, and we found three different ways in which we were able to make these two methods return different keys. So the first case is where in some implementations of this interface, method A, let's say resolve security key, supports a key type that is not supported by method B. So for example, resolve security key supports things like RSA keys, but resolve security token does not support this key. The second scenario is where you can actually have one of these methods that only process a subset of the keys in the key info section, while the other one is processing all of them. So this was the case, for example, in SharePoint, where when trying to resolve the security key, they were only accessing the first element of the key info section. And when trying to resolve the security token, they were processing, iterating through all the different elements. But the case that we are going to review today, because we don't have more time, is when both methods support the same key types, and they support the same subset of keys, but they process them in a different order. So we reviewed different frameworks within the .NET framework that implement these interfaces and that support and accept SAML tokens. But we don't have time to cover all of them, so we will focus on the WCF, which is used to develop web services, right? And we use that, for example, to exploit Exchange Server and be able to access any inbox, not just on-premise, but also on Office 365. So WCF is basically a framework to build web services based on the SOA architecture. So they are using SOAP envelopes, which basically are XML documents. What is interesting for us is that these web services accept SAML tokens for authenticating the clients. So if we can craft any arbitrary SAML token for any arbitrary user, then we are going to be able to authenticate into any of these web services. And that was the case for Exchange, for example. So if you look at the source code in this SAML assertion type, you will find this piece of code that basically represents what I told you before. So you have two different kits, two different methods. Resolve security key and resolve security token. Both of them are processing the same key info section of the token that is represented by the key identifier variable. And each of them return different elements. So because they return different things, they are doing different stuff. And if we can abuse that their implementation is different in order to return different elements of this key info section, then we will be able to bypass the verification process. So when dealing with the resolve security key, what they are doing is basically they are iterating through all the elements in the key info section. And for each of them, they are basically trying a number of resolvers. As you can see here, they are trying, this token resolver, then base, and then they are trying to create a key from intrinsic key class. So different resolvers. However, when they resolve the token, they are doing kind of the opposite. So the approach is very similar, but they start iterating through all the resolvers, and for each resolver, they try all the keys in the key info section. If one is not successful, then they move to the next one, right? So basically, they are iterating through all the same combinations of keys and resolvers, but the order is different, right? So what we have is basically something like this. What we need is basically a key in the first element of the key info section, which cannot be resolved by the first resolver. So then we will move and try key 1 with second resolver. If we send a key that can be resolved by this second resolver, then this method will return the key at this point, and then we'll stop processing the remaining combinations. So as I said before, key 1 cannot be resolved by resolver 1, so we will skip this one. But because the order of the iteration is different, now we will try key 2 with resolver 1, and this will be successful, so we will be returning key 2. So with that, what we can do is basically modify any existing token or create one from scratch, then sign it using our own private RSA key that we can generate, and then include the public key for this RSA key as the first element of the key info section. Then we will include the identity provider certificate as the second element that is public, is something that the attacker can get, as the second element of the key info section. And because of this difference in the way of resolving or iterating through all the keys, the resolve security key will return the public key for which the private key was used to sign the document, so the signature verification will be successful. And when resolving the signing party, it will use the expected identity provider certificate. So when trying and checking if they trust the signing party, they will get the identity provider certificate, and they of course trust the identity provider. So we were able to confuse them into using two different keys when they should be using just one. So in XML, it looks something like this. So you have first element is the injected key. This is the attacker public key. In this case, we were using RSA key, but you can also use other keys. And the second one is the expected key from the identity provider. So that was basically it. I think I'm out of time. You can find all the research in this GitHub repo, the white paper, the videos for the demos, also an extension for Verb if you want to try your web, your WCF services, for example. And that was all. So, I think if you have any questions, I will be around.
Okay, big thanks to Alvaro and all our presenters. And now it's time for us to network and chit-chat and have some drinks. Thank you.
So I think it was shorter than 15 minutes in the end. When I did like a dry run, it was like 16, 17, 18. So always on live.